Swayam Prabha. Digital India. Educated India.
In this lecture, we are going to now see a practical application of our knowledge of material properties for material selection for the heat exchangers. Okay. So, this is what we are going to see in this particular lecture. So, let us see how some of the thermal properties that we have learned earlier can come into picture in terms of material selection for a very important practical system called heat exchanger. Now, you know that why a heat exchanger is required, because it helps in terms of exchanging the heat between hot and cold fluid, okay, such that the heat flow per unit area is maximized. There are many applications, for example, in automobiles or even in simple room heaters. Okay, in many cases you need to actually either cool the system very fast or you need to heat it up very fast. In both the cases, you need to design a suitable heat exchanger to do this particular work. So, our objective here is to maximize the heat flow per unit area, and what are our free variables? The tube wall thickness and the material choice. What are the constraints that we may actually come across? One of them is the support pressure difference, maximum pressure difference delta P between the inlet fluid and the fluid outside, and this is important, up to what temperature it can withstand. Let us say in this particular example, we will keep it to be sufficiently high, 150 degrees centigrade, and also corrosion resistance can be another important point. We will keep that point in mind when we will finally select the material. So, let us go to the board and use the ASB criteria to do this same exercise. So, we have a heat exchanger. Let us first draw the heat exchanger. Suppose this is the surrounding fluid, and on the surrounding fluid we have a heat exchanger coming in, and which has a uniform diameter, and suppose this is what is our boundary. So, this is what is our fluid to boundary. This is our fluid to, and we have the fluid 1 inside. This is fluid 1, and we have the temperature here is T1, the pressure here is P1, the temperature here is T2, pressure here is P2. So, the same fluid is here all around the fluid 2, okay, and we also have this one with a uniform, say, diameter all around, say suppose T1, and if we cut across this tube here A, what we are going to see is that it has a finite thickness, uniform thickness, and this thickness is T. of the, that is the wall thickness, right, because that thickness will become important for us when we will analyze the system. Now then there are three things that we will be basically analyzing in it. One is that there is a fluid one inside here, right. So the first thing is the heat that is getting convected from this fluid one to this solid, then it is conducted. So this conduction, and again there is a convection. So there are the three elements that will come into the picture. So conduction, convection at the two other sides. So there are these combinations of convective and conductive heat transfer that is going to take place in the system. Now let us assume steady state heat flow. Okay. Let us just put our objective of course at the top, which is maximize heat flow per unit area. Okay. And let us now assume that steady state heat flow now the heat transfer between fluid 1 and the wall. Okay. So let this be denoted as Q1, which is H1A times delta T1, where H1 is the heat transfer coefficient. Of fluid 1. And then, so we should be able to find out delta T1 is of course the temperature difference between the fluid and surface 1. That is the internal surface of the fluid. The temperature difference is going to actually is delta T1. So that is what is my first part A, that is the heat transfer between fluid 1 and the wall, which is happening here. Next will be the B, that is the heat conduction, and next will be C. So let us look at the conduction. So heat transfer across the wall this can be written as, so this is our first equation. Now the second equation is Q2 equals to K A delta T over T, where we know that A is the surface area, K delta T is known to us, T is the thickness as I have shown here, that T is the thickness of the wall, and K is the thermal conductivity. Now, the last part C, so this is my second part. The last part C, which is heat transfer between the wall and fluid tube. In that case, Q3 is very similar, is H2A delta T2. This is my third equation. So, we have to basically get a equivalent expression of heat transfer on the basis of these three equations that come into the picture. So, if we keep these particular equations in our mind, then we can go for this equivalent heat transfer now. So, let us try to erase these parts now and try to get a formulation for the equivalent one which takes care of all these three things together. Now, one point we have to keep in our mind here, that at steady state these three, at the steady state Q1 equals to Q2 equals to Q3. Okay. So, that has been achieved, and hence at that stage the heat transfer, the average heat transfer at the steady state is 1 over UA equals to 1 over H1A plus T over Ka plus 1 over H2A. Okay. So, it is like you have three resistive systems and all first order, and all of them are together, that is the giving you the equivalent total resistance to the system. So, U here is the overall heat transfer coefficient. And it can be also written that the Q, the steady state is Q equals to UA delta T. Now, what happens is that in most of the cases this actually dominates the heat transfer, the T over Ka, and in comparison to that we can actually neglect these two. So, suppose in any particular case it is possible for us to do that. In that case, what we can write is that we can further simplify these expressions now, and we can write it as for the domination of heat conduction across the tube wall over convections, we can write that simply Q equals to Ka delta T over T, right. So, this we can say is the at the steady state overall heat conduction when everything else is actually neglected. Now, during this transfer of the fluid at pressure P1, this wall is also subjected to some stress, which is something like a hoop stress that is happening in the wall. So, it is expanding, trying to expand the wall. So, from the mechanical point of view, it has to withstand that pressure also. So, the stress that will come in the tube wall from the tube wall stress point of view, we can write that sigma has to be less than sigma y, and what is this stress here? That is delta P, the pressure difference, times R, the radius of the tube divided by T, that has to be less than or equals to sigma y. In fact, by keeping thickness as the free variable here, so thickness is here as a free variable. So, I can write that T equals to delta P times R, okay, or let us call it as R1 equals to our d1 by 2. So, delta P times R1 divided by sigma y. Now, I can substitute this in this equation of overall heat transfer. So, that means I can write here that Q equals to K A delta T times sigma y divided by delta P times R1, right. So, I can write also that Q equals to, let us keep all the other parameters separate, that is A delta T over delta P R1 and K sigma y. So, in a heat exchanger, if I want to increase the heat exchange rate, more heat to transfer from fluid 1 to fluid 2, so that either I can heat up fast or I can cool fast, I must increase this K times sigma y. That is, both K and the yield strength has to be increased, so that it can sustain the pressure. At the same time, the higher thermal conductivity allows us to take more temperature, to take more heat from fluid 1 to fluid 2. Now, let us look into that, what are the possibilities that are there for us for this particular system. So, now if we look into the ASB chart, we will see that in this particular case, because we have K over K sigma I. So, if you take a logarithm of the 2, that means if K sigma y is a constant, then log of K would become minus log of sigma y plus log of C. So, that means there is a negative slope, and that negative slope, considering the 150-degree temperature difference, will bring us in this particular line. Okay. So, the line with a negative slope, and if this particular line, now we actually look at it. So, this is the curve, this is a relationship between thermal conductivity and sigma y. With this negative relationship, all I have to see is actually see everything beyond this point, because everything below this point are not suitable for the heat exchanger design here up to 150 degree centigrade. So, if I magnify this part, what are the possibilities for us that is coming? You can have the brass UNS alloys, we can have aluminum bronze alloys, phosphor bronze alloys, nickel based alloys, silicon bronze alloys. So, these are the possibilities that comes in our particular slide area. So, if I look at it further, you will see that the brasses like naval brass, here the K sigma y index is the highest, 5 into 10 to the power 4. The only problem is for naval applications there is a de-zincification, that means it is susceptible to environmental pollution. So, that is why the corrosional point of view this is not a good idea. Phosphor bronze 4 into 10 to the power 4, it is cheap, but not as corrosion resistant as the next one, that is the aluminum bronze, which is slightly lower 3.8 into 10 to the power 4, but it is economical, it is corrosion resistant, and this comes out to be a more practical choice than the brass or the phosphor bronze from the corrosional point of view. Nickel iron aluminum bronze is actually more corrosion resistant, but it is more expensive, and this also is little less. Similarly, silicon bronze is less good because its index is less. So, out of all the choices, as we can see that the first three are better choices from the material index point of view, but if we put corrosion as the constraint and also economy as the constraint, then aluminum bronze wrought is coming out to be the best choice, and that is what is generally used in the heat exchanger design. In the next lecture, we will learn about the electrical properties of the system. Thank you.